All right, Mathlers, here is Chapter 2A, Evaluating Indices, and 2B, Index Laws. Okay, so indices happen when we're dealing with multiple multiplications. So if we have repeated multiplication in this case, we can write this using indices, where 4 is the power or the index there, and it's a superscript, and then the base is here. So 3 times 3 times 3, if we have repeated multiplication, we can write that as 3 to the 4th. Okay, so in general, I'd make sure this is what you want to write in your notes. If n is a positive integer, then a to the n is the product of n factors of a to the n is the same thing written out. So the indexes is going to help us abbreviate that. So if we want to know what 2 to the 5th is, that's the same thing as 2 times 2 times 2 times 2 times 2. Well, that's 4. 2 times 2 is 4. And then I can think of it as this. And 4 times 4 is 16 times 2 is 32. So that's 2 to the 5th. I can also do it with writing this out like this. For example, 2. 2 to the 3rd is 2 times 2 times 2 times 5 squared times 7. So that's written out. 2 to the 3rd is 8. 5 squared is 25 times 7. That's 25. So we get 25 times 8 is going to be 200 times 7 is going to be 1400 or 1400. Okay, so let's go to example 3. So by dividing continuously by prime numbers, we can rewrite 504 as a product of prime factors in the index form. So I always start with my even numbers and I say, all right, 504 can be written as a product of 2 and 252. It's still even, so I can break it down into 2 again. And 252 divided by 2 is 126. Break it down into 2 again because it's even, and I'm going to get 63. At this point, I can't divide by 63, so I'm going to recognize I know my factors of 9, so this can be broken down into 9 times 7. So notice I can stop when I see prime numbers. So 2's prime here, here, and here. 7's prime, so I can stop there. And then 9, I can break it up into 2 factors of 3 and 3, which 3's prime and 3's prime. So now I have my prime factors. So 200 or 504 can be written as 2 cubed times 3 squared times 7 to the 1st is equal to 504. Okay, so we can go to a next example here. So negative bases. So negative bases raised to an odd power is always negative. A negative base raised to an even power is positive. So often you learn that a negative times a negative, so negative 2 times negative 5 would be a positive 20. I'm sorry, a positive 10. And what happens is we think of it as the negatives canceling out. So for that same reason, anytime we have an even power, we're always having negatives cancel each other out, because when you have even numbers, you always have a complement there. So negative 1 to the 1st is negative. Negative 1 to the 3rd is negative. And then you can notice that negative 1 to the even powers are positive. Okay, and that goes the same regardless of the base. If the base is negative, it alternates. So with a odd power up top, you get a negative answer, and you have your positive answers when you have even indexes. Okay, so our next one, look at these. So if we have negative 3 to the fourth, well, I know that 3 to the fourth is equal to 81. So negative 3 to the fourth is going to be equal to 81. Doesn't change whether it's negative 3 or 3 to the fourth because we have a even index here. Now on B, because our negative 3's not in parentheses, we can interpret this as negative 1 times 3 to the fourth. So we must do our exponents first. So 3 to the fourth is 81, but that's times negative 1. So our answer here is negative 81. Notice in this scenario, in B, we have a negative outcome. In this scenario, in A, we have a positive. So the presence of those parentheses will make a difference. Okay, so let's look at here now in C and D where we have odd indexes. So negative 3 to the fifth is going to be 243. But because it's odd, this will still be negative because negative 3 to the fourth is positive. Then when we multiply it, this 81, right, by negative 3 once more times, then it goes back to being negative 243. So in D, again, if the negative's on the outside of the parentheses, kind of similar to B, we have negative 1 times negative 3 to the fifth. Well, from our previous example, negative 3 to the fifth was negative 243. So if I multiply a negative 1 by a negative 243, that becomes positive 243. Okay. And our next slide here is we're going to talk about some index laws. So we're going to look at some of the patterns here on this slide, and then we're going to look at the rules that these create. So if I'm dividing a to the fifth like bases by each other, notice I can write a to the fifth as a times a 5 times, a to the second those times. Okay, so if we cancel those out, what we're going to see is that what we're left with is just 3 a's, or a to the third. So that's going to generate a rule that if we have a to the fifth up here and a to the second down here, this was equal to a 5 minus 2, which is equal to a to the third. So we can subtract those indexes when we're dividing. So a cubed squared, well, if we're squaring something, we're multiplying it by itself. So this is representing a cubed. This is representing a cubed because it's squared. Well, altogether, how many a's are we multiplying together? That's 6. So we could see here, if we wanted to simplify this, that a cubed to the second power is equal to a 3 times 2, where we can multiply those indices there. Okay, here with a times b squared. Okay, well, a times b, something multiplied by itself, it's here. Then we got to remember from our distribution property that a times a is there. Then you do a times b. Okay, and well, because there's no addition or subtraction, it's all multiplication across. So what we get is a squared b squared. And we don't necessarily have to double multiply here because there's no presence of an addition sign there. So really we just write it out like that. We can rearrange them and we see that we get a squared and we get b squared there. Okay, so if we have fractions being raised to an index, we can simplify it as this. But notice this is just rewriting it out. We can do a times a times a, and that's written here. And then we can do b times b times b, and that's written here. So notice what we can do is we can just distribute this through to the numerator and our denominator, and we get a cubed b cubed. So on this next slide, we have a bunch of rules that are going to be very important in this unit. I'd go ahead and pause the video at this point and record these down. Okay, now that you have them recorded on, let's put some of them into practice. Okay, so if I have a to the fourth times a to the fifth, I know that the rule states that this is going to be a of 4 plus 5, which is equal to a to the ninth. And I don't have to write them all out. The rule here states that because I'm dividing, I can do 7, 8 minus 5, and I'm left with 7 to the third. On example 7, because I'm writing x cubed to the fifth power, that's going to be multiplying 3 times 5, so it's going to be x 3 times 5, and that's going to be x to the 15th. Okay, so those are just utilizing these rules here, right? So we utilize this one, we utilize this one, and we utilize that generalization. Okay, so let's look at some other examples. Okay, anything divided by itself, so if we subtract this out, we get y to the 0. Anything to the 0 power is always 1. Okay, if I multiply these out, I'm going to multiply together my coefficients, so I'm going to get 15. Then I'm going to multiply my x's together. Well, this is addition, so it's x 2 plus 5, because they're like bases, so this simplifies to being 15x to the 7th. Okay, in example 10 here, I'm going to simplify my numerator, so that's going to be adding b3 plus 7. Okay, notice the base is different. It's a power to a power. So I'm not going to add 2 and 4, but I'm going to multiply 2 and 4. So what I'm going to do is 3 plus 7 is 10, so I get b to the 10th numerator. My denominator is going to be b to the 8th. Well, now I can utilize the second power and reduce them and say this is b to the 10th minus 8, which will end up being b squared. Okay, and the final examples here. So we're going to continue. This is going to utilize some distribution. So here, in simplest form without brackets, so notice the 2 and the x are both in the getting cubed, so I got to make sure the 2 gets cubed, the x gets cubed, and also my denominator, the y, gets cubed. Anytime I have a number that's being raised to a power, I'd want to simplify that. So 2 cubed is 8, x cubed over y cubed. Okay, the next one, I'm going to simplify number 12, and so I'm going to see it's a power raised to a power, so it's going to be x 2 times 3 over 2 cubed y cubed. This is 2 times 3 is going to be x to the 6th over 2 cubed again is 8 and y cubed there. X's and y's are different bases. I can't simplify those. So that's as far as I can get. Here, 2 to the 5th, okay, I can think of this as two things. I can raise it to the second power, and then I can raise it to the first power. So I'm going to work from the inside out. So 2 squared is 4, 5 squared is 25. So I've taken care of the 2 part of it, but I still have the -1 on the outside. Well, -1 says I can reciprocate that or flip my fraction. So I'm going to get 25 out over 4. Notice by doing this, I'm accounting for this by flipping it, so I don't write another index there. I'm just going to leave it blank. Okay, that concludes our notes for today. Make sure you highlight any questions you may have.